Hey guys, welcome back. We're going to be looking at our navigation bot for World of Warcraft. So here I've got my bot open. It's looking for the target. It's not able to find it. So let me pop open an image. And you can see here I just have a screenshot. So it's looking for this navigation beacon. It's found it. So we've got our location. This is all the work that we did last time. It's got our location and it's got the percentage match. In this case, it's not exactly 100%. That's because I'm using a screenshot, but that's okay. So it's close enough that it's able to find it. Now what's new is we've programmed it so it's able to detect the angle of our player with respect to that navigation beacon. So for example, if I move this over to the left-hand side, that indicates that my player is about 50 to 60 degrees away from that navigation beacon. And if I slide this thing to the middle of the screen, you can see that it's about, gets close to about 0 degrees. So facing that. And if I move to the right-hand side, you'll see a negative angle. Now, the reason you see this image moving is it's not because I'm pressing any buttons. Actually, the bot is also now programmed to try to turn our player to face that beacon. And the reason that it's moving that image around is that the same keys, the arrow keys, are actually tagged to moving the player. They're also tagged to panning my image around. So it's trying to look to the left, and by doing that, it's actually panning the image in that direction. So that's what's happening. So you can see if I slide this image back over, it's going to try to keep hitting the left arrow, which pans the image to the left, and it keeps moving that navigation beacon to the right. So that's pretty cool. So you can actually see it working right now, even though we're not in game. And in addition to our rotation with respect to that navigation, we also have our pitch. So if the target was way up above us, we would want to know that. So what we can actually do is you can see that we actually have a pitch angle here. I called it pitch ratio. I got to fix that. It's really an angle. And if I put this down here, you'll see that it'll be a negative angle. And if I move it up top, oops. And if I move it up top, it's a positive angle. So negative angles are down, positive angles are up, positive rotations are to the left, negative rotations are to the right, and we'll be able to use this to control our player with a lot of accuracy. So before we talk about the geometry and the coding, let me show you an example of this in game. Okay, so here I am in game. Now what's going to happen is I've programmed the AI so that it tries to keep me within about a 10-degree arc of the target. So it doesn't have to be exactly 0% tolerance, because we don't want this thing to be constantly twitching. But once we're in about a 10-degree arc, it's going to consider that a match. So what I'm going to do is first I'm going to rotate away, and you'll see I'll take my hands off, and the bot's going to try to move towards that target. And this is where, so I haven't really spent a lot of time optimizing this yet. So what we're probably going to have to do is, based on the distance of that angle, we're probably going to want to rotate more or less. We're going to want to scale that. So I haven't gotten that fancy yet. So right now it's just bumping us in that direction. But what's kind of cool is if I just strafe to the left, and as I do that, it's going to obviously cause that angle to change. If I hold the strafe key down, my player's going to keep continuously trying to turn towards that. So I'm just holding the strafe button down, and you see that once I get out of that 10-degree arc, he kind of pops over in the direction of that target. So that's pretty cool. Now I noticed a couple of things about the target. It actually appears as no matter how close you are, as long as there's something obstructing your way. So you can see right now I'm only 50 yards away, but it still sees it. It's still trying to pop in that direction. But if you have direct line of sight with the quest giver, it only appears if you're at least 70 yards away. So that's some good information to have. So right here, see how I just got out of 70 yards? Now if I move this over here, he's going to try to align himself. Okay guys, we're going to do one quick geometry lesson here, refresher. Unfortunately, we got to do a little bit of math, a little bit of geometry. So if this is my screen, and I have a target on it, so we're going to use this yellow diamond. This is our target that we've been talking about. That's somewhere on the screen. It could be anywhere on the screen. We can imagine that our screen has a center point, And of course, this is our player. I'll draw our player here in black. So this is our player. He's standing there. I know it's a very good drawing. Thank you, thank you. Now, we want to calculate the rotation of our player towards that target. So to do that, we basically want to calculate this angle here. So this angle here that I'll call alpha. Now, if you remember from geometry class, tangent, tan some angle is equal to opposite over adjacent. Opposite over adjacent. So we're going to use that, we're going to use the arctangent to calculate the angle here. So we have a triangle that looks like this. So let me draw this over here to the side. So this is our vector to the object, and we have a right angle, of course, and we're trying to solve for this angle alpha. So what we want to get is we want to get the opposite. So this is opposite to that angle. And this is our adjacent on the side here. This is the adjacent here. So what we can do is we can calculate this angle by using these two lengths here. The length of the opposite side and the length of the adjacent side. And the length of the opposite side, in this case, is the difference in width. This is our delta width. And the distance here on the adjacent side, this is our delta height. So we know that this point here at the absolute bottom of the screen is 1/2 our width, because it's half the width of the screen, comma our height, our maximum height. Since the screen height goes in this direction, this is pixel 0, 0. And in my case, this would be 1920 by 1080. This is my width. Okay. So what we know is that this point down here is half width height. So that's 1920 divided by 2. What is that? 960 by 1080. That's this point down here. We know the point here. We know the point here to our target because that's what we calculated in our last video. So all we have to do is calculate the difference in x, the difference in y, and we can use this formula of opposite over adjacent. So we can do a tan, and we're going to put in our dx divided by dy. And this will give us the angle alpha. And the angle alpha is the angle difference between our player looking straight ahead and wherever that target is on the screen. So if the target is over to the left, let me erase some of this stuff now. So again, I'll draw our player here. And here's our target. We'll say that's our target. So, and this is of course straight in front of our player. So this will be a positive angle. And this would be a negative angle. Okay, so counterclockwise is a positive angle. That's going to give us a positive number. And counterclockwise is going to give us a negative number. So in this example that you can see here, this would be our vector. Let me draw it in green. So this would be our vector. And in purple here, this would be our dx. And in orange here, that would be our dy, our difference in height. And we could use the formula a tan dx over dy. And that would give us this angle right here. That gives us the angle to that target, okay? So now we're going to go and we're going to actually program this and test this together. So let's get coding. Okay, the first thing you want to make sure you've done is you've added these parameters to our bump functions. If you remember in the last video, I mentioned that I was going to update all of them. So make sure you do that. The parameter will essentially be a time, and it will be the time that we want to hold the key down. And the reason we want to parameterize this is I was doing some playing with the bumps, and 0.05 isn't perfect, and we're going to want to, use this throughout the course of our project. So just make sure you have a parameter here. We're going to use that later. Okay guys, next I want to create a new file that I'm going to call nav.py. Nav.py is going to contain a lot of the navigation related functions that we're going to be using. So I've got nav.py created here, and this is where we're going to be doing our geometry calculations that we just talked about. So let's import math. We're going to be using some functions from math like the arctangent. And we're going to create two functions. We're going to create a function called getNavTurnAngle, and we're going to pass in our nav location, which will have our x and y coordinate that we calculated in the last video. That's the x and y coordinate of our nav beacon. And also we're going to want to have our width and height, the width and the height of our screen. But of course, this is going to be standardized, or this can be created as a setting. So I'm gonna hard code mine in as a default, so I don't have to provide this all the time. But this makes it a little bit more flexible. So in my case, my screen resolution is 1920 by 1080, and I'm just going to put pass in there for a moment. And we're going to create another function that I'm going to call getNavElevationAngle, and it's going to take the same parameters. Okay, so these two functions, the first function is going to be used for calculating our turning angle, and the second function is going to be used for calculating the elevation angle difference, which I haven't programmed in. We're not using this yet, but it's probably something we're going to eventually use, so we might as well just create the function right now. So let's create our turning angle. So the first thing we want to do is we want to calculate, if you remember, let me erase all this junk here. Okay. So if you remember, we need to, this is our screen. So in my case, this is 1080. This is 1920. So that's pretty simple. Now, if you remember, we have to have a couple of key points. So this is our nav beacon that we called nav location. That's the location of our nav beacon. But we also need to program in, for calculating this angle, we need to program in this coordinate. And if you remember, this coordinate is 1/2 the width by the height. So that's what we have to program in. So here I'm going to say that my center width is equal to basically my width divided by 2. Now I'm going to use the // operator. That's the floor operator. So basically what that will do is when you do a division, it will ignore the remainder. This is good just in case. It's probably not going to be the case, but if your resolution resulted in and not a whole number, it would basically discard the non-whole amount. So that's just kind of a convenient way to do that. It's called floor division. And then we want to calculate, if you remember, we want to calculate our dx. So grab the pen. So this is our dx, and this is our dy. And basically, it's just going to be the difference between our points here. So let's do that. So our dx is going to equal to our nav location 0. So that's the x coordinate of our nav location minus our center. And our dy is going to equal the nav location 1. So that's the y component of our nav location minus the height, because remember, this we're using the whole height here for the bottom of the screen. Okay, so now we have our dx and our dy. Next, we can easily calculate the angle. So the angle is going to equal to a tan 2. Oops, sorry, math. We got to use the math library. A tan 2, and we're going to put in this takes two parameters, the numerator and denominator. So we'll put in the numerator first, so dx comma dy. So that's the same as doing this. So that's the same as doing a tangent of x over y. Okay, just the x is the first parameter and the y is the second parameter. Now, if you're wondering why we're using a tan 2 instead of a tan, we could use both, but the only difference is that the a tan 2 will keep the negative components. So for example, if I have a circle and my angle is this direction, by having the a tan 2, this is a negative x, negative y. By using the a tan 2, I'm able to differentiate the negative x, negative y from the positive x, positive y. So it maintains that positive negative relationship, just for your information. So that's our angle, a tan 2. And then what we want to do is we want to divide that, or do the modulus operator by math.py. And the reason is that if this is bigger than pi, so if you remember the maximum angle that you can have is 2 pi in a circle. And so if we get an angle like this, we don't want this angle. We really want to get this angle. So we can do the modulus with math.py there. So that's just going to make sure that we don't have more than a pi angle. And then what we want to do is we want to say if our angle is greater than math.py over 2, then we want to do our angle minus equals math.py. And then what we'll do is we will return this angle. And this is going to be in radians. So keep in mind, these angles are in radians, not in degrees. And now we can do the same thing for our elevation function. So our elevation function is going to be very, very similar. So again, I'll just draw this in a clean screen here. The only difference is that we're going to be using this point here. So remember, this is now going to be our maximum width by half of our height. So that's our point here. And then we're still going to be finding some point here with a vector. Oops, I'll make that green. And the only difference is this time we're going to be using dy over dx instead of dx over dy. So otherwise it's pretty much the same. So we can say our h center is equal to h divided floor division by 2. We can do the same, dx equals nav location 0 minus our w. We're using the max w this time. And our dy is the nav location 1 minus our h center. Okay, that's our dx or dy. Now we're going to do the same. We're going to do angle equals math dot a tan 2. This time we're going to do dy over dx. And let's do a modulus math.py. Make sure it's not more than a pi angle. And what we can do is we could say if angle is greater than math.py over 2.0, then angle minus equals math.py. And let's return this angle. Again, these are all going to be in radians. So these two functions are going to basically take our nav location, assuming a fixed width and height, and make sure your default parameters here match your resolution if it's different. But it's basically we're going to plug in our nav location and we're going to spit back out these angles. So this is very convenient. So let's go back to screencapture.py and let's start to use this parameter. Okay, so we've done most of the heavy lifting now, guys. So here I am back in agent screencapture.py. So we want to make sure that we import our move function, our move Python file, since we're going to be using moves now. Before, all the movements that you saw were done in the debug section down here. So now we want to actually start calling that from our main agent. And we also want to import the nav file that we just created that has the relevant functions. And let's scroll down in our capture screen until we get to if self.enabled nav. So if we're doing navigation, we want to do these activities inside of that block if our navigation is enabled. And what we can do is, first we want to check, do we have a nav location? So what we don't want to do is we don't want to try to perform calculations on something that's a none type, because remember, this nav location is a none type by default, and it's also none if there's not a close enough match. So we want to check to make sure that it exists. So we can actually use the fact that it's a none type to determine does it exist. So we just say if self.nav location. So if a nav location exists, if it's not none, then let's go ahead and start executing our code. So if it exists, first let's calculate our turn angle. So we can do our turn angle. Let me move this over. It's going to be a little bigger here. So our turn angle is going to equal np.round, because I'm gonna round this off, and we'll say nav. So we're calling our navigation file that we just created, and we're going to call get turn angle. That's the function we just created, and we have to pass in our nav location. So that's going to be our self.nav location, and that's going to return our angle in radians. And then I'm just going to round it off to 2 decimal points. I don't really have to do that. Okay, next what I want to do is I want to calculate the pitch angle doing the same thing. So we'll say our pitch angle, this is our elevation angle, I'm calling that pitch, is np.round nav.get elevation angle, and we'll do the same thing. We're going to put in self.nav location, and we'll round that off to 2 points as well. Okay, so now we have our angles, and we want to actually display those on the screen. So this is going to be very simple. We're just going to copy and paste in our cv.putText function here. Let me tab this over. So this is the first one. So we'll say our nav turn angle is going to equal to this turn angle. So we're going to put in our turn angle. So let's actually convert our turn angle into degrees, since it's a little bit more intuitive for me mentally when I'm thinking in degrees, although radians is also convenient, but let's save it as degrees. So to convert radians to degrees, we're going to do 180, so times 180 divided by pi, and I'll just hard code it in 3.14 since it's kind of an estimate. So you can remember that formula. If you want to convert from radians to degrees, it's times 180 degrees divided by 3.14, and vice versa would be 3.14 divided by 180. So now we have this angle in degrees. We have our pitch angle in degrees, and we're going to say our turn angle is this, and we can say, instead of this, we'll just say degrees here. And let's shift this down by 50 pixels. So we'll set this at 250 pixels. And let's keep it green. And let's do the same thing for our pitch angle. So here's my code for my pitch angle. So I'll just call this nav pitch angle. And let's put in our pitch angle. And let's shift this down by 50 pixels as well. So now I'm at 300, and we'll keep it green. And let me run this code and see if we are able to see these angles yet. Let's test this out. So first let me open up the code. Let me run the process. Okay. And let me open up a image. Okay, excellent. So it looks like we're working. So when this is close to the 0 and the horizontal, you can see we're close to a 0 degrees. If I go up, I'm at 6 degrees here, so you can see that the angle is increasing. And if I go down, it's negative. Let's look at the turn angle. So I've got 0 degrees, that looks good. If I go to the left, that looks good. That's about 45 degrees. If I go to the right, that's, let's see, I'll move this over here. If I go to the right, you can see I'm at around a negative 50 degrees. So that looks good. Okay, so let's go to our turn area here. I'm just going to add a little bit of space here. And what we'll do is, that's a little bit too much space. What we'll do is underneath of our turn angle and underneath our pitch angle, after we've already calculated those, we will attempt to do a movement here. So we're going to use our bump. So we're going to say if our turn angle is greater than 10. So basically, if we're not within 10 degrees of that object, we want to do a bump. So if our turn angle is greater than 10, then so greater than 10 again means that it's to our left. We want to turn left. So we're going to say bump, we're going to say move.bump left. And I tested some different values here. And what I found was 0.01 worked pretty good actually. So like a pretty light tap. Now we want to get eventually more sophisticated. So we're going to look at how far off we are and we're going to turn with some ratio to that, but I haven't worked that out yet. So, but conceptually, you can understand how easy that would be to implement. And we'll do if our turn angle is less than 10. So if we have less than minus 10. So if we're less than minus 10 degrees, then we want to go to the right. So we'll say move.bump right. And same thing, 0.01. So let's test this out now. I'm going to run this code again, and I'm going to put the image on the screen, and let's see if it's working. And there you go. You can see that it's trying to move that image. So it's moving it to the it's moving it to the right because it's like our character is turning to the left. So that looks good. And let me put it over on this side. And you can see now it's trying to turn our character to the right. So congratulations, guys. You have implemented something pretty awesome. We have implemented a bot now that is able to detect its orientation with respect to the location of a quest tracker. And we're able to turn our character in the direction of that quest tracker. That's awesome. So congratulations, guys, and I'll see you in the next video.